Hey all, so this is going to be section 5.4, which is going to be right triangle trigonometry. It is actually covering things that we've seen in the last couple sections, but looking at it from a little different perspective. And so if you think about let me get my pen going here. Could have done this before. There we go. If we think of our definition that we had before, sine we defined as y over r, for instance. And so this time, instead of using x's, y's, and r's, we're going to use adjacent, opposite, and hypotenuse. And so the hypotenuse, remember, for a right triangle is always the longest side. It's the c when we're doing a squared plus b squared equals c squared, and it's going to be opposite the 90-degree angle every time. And then we have the two legs of the right triangle, and when we have an angle here, in this case they're using t, but it could also be theta, the adjacent side is the side that's touching the angle, and then the opposite is the opposite the angle. And so here, this is still, it's opposite over hypotenuse, which is the same y over r that we were seeing back in section 5.2. It's just now we're giving it a little bit different naming strategy. And there are good reasons for having kind of both systems, both the unit circle that we saw in 5.2, and then this, what's called right triangle trig, in 5.4 here. And I'll just do a quick little example as to why. First off, this a right triangle is limited to 90 degrees, and we have more degrees than that. The circle goes around 360. So the right triangle trig is limited in that it doesn't allow for angles larger than 90. And so, like, if I had a 120-degree angle here, there isn't a hypotenuse on that because it's not a right triangle. So that's one way the unit circle is good. Another way is when we go to solve trig equations later, and let's say we're solving the equation sine theta equals 1/2 on the interval 0 to 2 pi inclusive. You don't have to quite know what that means yet, and that's totally fine. But this has two answers. This is asking what angle would make sine come out to 1/2. And remember that sine is our y, and then 0 to 2 pi means in one revolution. Sine is our y value, so there's a point here where sine is 1/2, and there's another point over here where sine is 1/2. And if we're looking at this triangle, like, you can't see that at all, and it doesn't make sense why there'd be two answers to these things. So the unit circle is good there. When we go to graph these in, I think, the next section after this, the unit circle is totally critical for getting this thing graphed and understanding why the graphs do what they do. And that said, sometimes the adjacent, opposite, and hypotenuse notation is super handy. I just pulled up a physics free body diagram real quick here. If I were going to try to figure out what this length right here is, which is a really, really common thing to do in a physics application like this, is this thing the x or the y? Like, that is really hard to tell. You have to, like, define your coordinate axes to figure out what that is. But if I know that this is theta, I know that that's opposite, and I'm right there. I can tell exactly which trig function to use, rather than kind of overthinking, okay, so this thing's now on a plane, but my triangle's been flipped around. And we'll see, like, by the second example, this gets really handy. As soon as you start moving these triangles around, it gets harder to think of it in terms of x and y. So they both have a place, and yeah, that's the reason for having kind of two sections covering the same idea. Let me talk about SOHCAHTOA. If you've ever taken trig before, you've probably heard of SOHCAHTOA. It's a mnemonic device for memorizing sine, cosine, and tangent. So S-O-H, stands for sine is opposite over hypotenuse, ka is cosine adjacent over hypotenuse, and tangent, TOA, is opposite over adjacent. And again, this is our same x over r and y over x that we've been seeing. We're just giving it a different naming strategy. So that's as much as I'll say there. If you want to see a really good discussion of putting together these two definitions, check out Leo's video. He does a whole proof on how those things go together. Likewise, when we get down to, there's three things we're going to look at here. one, just using SOHCAHTOA to evaluate trig functions like we've done. Two will be cofunctions of complementary angles. He does a really good explanation as to why these identities work. I'm just going to probably use them in this one because there's already a video up for the explaining the proof of the identity, and Leo does that really well. And then we'll use this right triangle trig to solve some applications towards the end of the section. Okay, so let's look at this first problem. In this one, we're given that B, this side right here is 5. Let me get that labeled. Oops. It's going to do this. There we go, 5. And we know that C is 13. Okay, I'm going to end up not writing on this thing because it's just super annoying. So we know 2 of the sides, and we're asked to find the ratios. The sign of in our angle is A, is what we're working on. And so we're asked to find all of these ratios for all 6 trig functions. So I know 2 of the sides, so we can go back and use, let me just erase these little dots I have everywhere now that, come on, do it. There we go. Erase that. That I know 2 of the sides means I can find the third side using the Pythagorean theorem, so let's do that over off to the side here. So a squared plus b squared equals c squared, and in this case I know b and c, which will allow me to solve for a. So a squared plus 5 squared would be 25 equals 13 squared, and 13 squared is 169. And then we'll subtract that 25 over when we get a squared equals 144. And then taking the root of both sides, I get a equals 12. And in this case, we're talking about the length of a side, and so we'll use the positive 12. We're not on the unit circle where we might have to figure out which direction we're heading. So sine is, I think I'm just going to do these off to the side so that I'm not having this picture bounce back and forth. So sine theta is going to be opposite over hypotenuse, and that's our SO of our SOHCAHTOA. And that will be the opposite side on that is A. Let me at least get that labeled as 12, so I can point at it. So annoying. So opposite would be 12 over 13. Let's see if I can manage to do this. I really can't. For cosine, that's going to be SOHCAH, so C-A-H. We'll get rid of that. So adjacent over hypotenuse. And our adjacent side is 5. That's adjacent to this angle A over 13. So that will be our cosine. And then TOA. So tangent is opposite over adjacent, and opposite is 12, and adjacent is 5. And then to get our reciprocal trig functions, remember that cosecant is the reciprocal of sine, so that one's going to be 13 over 12. Secant is the inverse, the reciprocal of cosine, so that's going to be 13 over 5. And cotangent is going to be the reciprocal of tangent, and so that's going to be 5/12. I think that's the one time I was going to try to write on the picture, so that's now done. So pretty straightforward. Once we have 2 sides, we can solve for the third, and then use our ratios to get all 6 trig functions for some given angle. So for the second problem here, solve for the unknown sides A and C given the triangle, this thing. So we know we have a 60-degree angle here, and we know this side is 7. So this is a good example of, so C is always the hypotenuse. It's the radius, so to speak, in terms of the unit circle or what we're looking at in 5.2. But is this one X or is this one X? And so that's, once you flip this orientation around, trying to define these as X and Y and figure out, are you looking at sine or cosine, gets way more difficult. If we just think of it as opposite and adjacent, it's much simpler. So for this one, I know I have an angle, and then I also have the side opposite that angle. So I want to use, when I'm looking at these, I want to use something that has opposite in it, because I know that. I don't know the adjacent side yet. So I want to either do sine or tangent. And they're going to get me, if I use sine, I'm solving for the hypotenuse. If I'm using tangent, I'm solving for the adjacent. I'm eventually going to do both, but that's how I know which trig function to go for. It depends on what I'm given. So let's start off with tangent of 60. And that's going to equal, so tangent, remember, is TOA, so opposite 7 over adjacent, and that's the A, because remember the C is always the hypotenuse, so this side, and it's opposite 90, so 7 over A is what I will need to solve. So tangent 60, when they give you a nice number like that, they're going to be looking for an exact answer on the homework. We'll see some coming up here where, you know, this will be 22 degrees, and in that it'll tell you to give it to so many decimal places. But for this, we would be looking for an exact solution. And then just as a reminder of our 30, 60, 90 triangles, so there's a 60, and this is 1, 2, and root 3. And tangent is going to be opposite over adjacent, or y over x. So tangent of 60 is going to be square root of 3. And 7a. So now multiply up the a, and I'll divide out the cube root of 3, and that will give me a equals 7. So multiply a by both sides, divide square root 3 by both sides. We have this. And then I'm going to go ahead and rationalize that denominator, just because sometimes the computer gets picky about that. And that gets me a is 7 root 3 over 3, because root 3 times root 3 is 3. So that got me this side, but now I still need to solve for the other side, which would be c. So I could use, I now know I have the adjacent and the opposite. The adjacent's kind of an ugly number, so that makes me not want to use it. So for that reason, I could use cosine, but I'm going to use sine of 60. And that's going to equal, so remember, sine is so. So that means we need opposite, which is 7, over the hypotenuse, which in this case is c. And if I had used cosine, I would just have to use this number instead of the 7, and the 7 looks like it'd be easier, so I'm doing that. Sine, remember, is it's the y over the r, so that's our root 3 over 2, so let's get that put over here. And that equals 7 over c. Let's go ahead and multiply both sides by c. And then we have root 3 over 2 times c equals, those canceled, 7. And then to get this out of there, I wanted to show that step. We're going to multiply by the reciprocal on both sides to get this down to a plain c. And now that all cancels, and I have c by itself. So I end up with 14 over root 3. And then we should probably rationalize that denominator as we do. And we go root 3 over root 3. And that's going to give us 14 root 3 over 3. If you look at the notes on this problem, you'll see I also, after this point, pointed out you could also use the Pythagorean theorem, because we would know, in this case, a squared plus b squared equals c squared, and so I know a is this number, I know b is that 7, and I could put that in and solve for c. I did that math in the notes. You can check it out if you want. To me, that got a little clunkier than just using the trig functions, but it is there in the notes if you want to see that version. I would probably stick with the trig functions. It's usually easier than trying to drag it through this, but both ways do work. Okay, let's take a look at this next one. So solve for x, maybe not be drawn to scale, round to 3 decimal places. Yeah, so here's where we're getting into the land of not as nice numbers. Let me see if I can. No. So this one, in case you're having a hard time seeing, this is 119 right here. This angle right here is 74 degrees. This one is 28 degrees. And our goal is to find the length right here. So the way I looked at it was I decided I was going to call this distance x1. So from right here to right here, calling that one x1. And then I decided, so that's one of my right triangles, is that little one. And then I have a big right triangle right here. And so I'm going to call that length x2. So this is going to go the whole way across. And so hopefully you can see if I go x2, scoot this over here, minus x1, that's going to give me this x that I'm looking for. The whole way minus that little piece is going to give me this. And so if I can figure out the length of the big triangle and the length of the smaller triangle, I can take the difference, or the sides of those, sorry, I can take the difference and get the thing that I'm trying to get to. So for this one, we have an angle and we have opposite again, and I'm looking for the adjacent side, so that absolutely sounds like, remember, tangent theta is opposite over adjacent. And those are the two things I'm working with, so that's why I'm using sine as opposed to, why I'm using tangent instead of sine or cosine, is because this has the sides that I both have and am interested in working out. So let's do x1 first. So tangent of 74 degrees is going to equal the opposite, which is 119, over the adjacent side, which is the thing I want to know, which is x1. So I'll multiply that x1 up and divide the tangent down, and that's going to get me to x1 equals 119 divided by tangent of 74 degrees. Scoot this up a bit. And then from there, I threw it into a calculator. The directions were asking for 3 decimal places, so I'm going to jot this down to 4 decimal places just so I have a spare one there so that when I round at the end, it's hopefully accurate. And that came out to, let's see, 34.1227. So now I know the short side, and now I'm going to get of the small triangle, and now I want to get x, this side of the big triangle. And so for that, I'll just do the same thing, but now it's going to be tangent of 28. So here's my, and there's my opposite, is equal to still 119, because it's still that same side, over, and this time I'm calling that x2. And so again, flip-flopping those around, I'm going to get x squared equals 119 over tangent of 28 degrees. And I threw that in the calculator, I got 223.8064. After that, I can say this number, which is our x2, minus this number, which was our x1, and then what that got me, I won't rewrite those, so I'm just putting this here and that there, and then that came out to 189.684 when I threw that in the calculator. So yeah, that would be that one. Get this scrolled up. Okay, so then we're going to do a few where they didn't give us a picture. I encourage you to draw a picture. At least for me, it really helps to get things orientated. So this one we got A is 5, angle A is 60. And not sure that I said it at the beginning, but let me go back and make sure I point that out. I think we have seen it in the previous section, but I can use this picture. We would call this one, when we have angle A here, the opposite side is going to be A. When I have angle here, and this one must be B because it's A and B have to be the legs of the right triangle. That would make this side B, and then the 90 always goes with C. So just in terms of how I'm labeling things on this next one. So let's see, we have a 60 degree. Let me draw this over here. So I know that's 60 degrees. And then over here we're going to have A equals 5. And so I'm asked to find the missing side. So I want to find B and I want to find C. So I know an opposite, and I want to find either of these. And so I can use, again, it's going to be sine and tangent are probably going to be the useful ones. Once I have the adjacent side, I could use cosine as well if this number came out nice. But just kind of looking for a place to start, I started with sine of 60 degrees is going to equal the opposite, which is 5, over the adjacent, which is C. And then remember from up here, let me just grab that. For sine of 60, sine is the y over r, so that's root 3 over 2. And as you do more of these, that will become more familiar. So I'll replace sine 60 degrees with root 3 over 2. And that gets me 5 over c. So we'll bring the c up and then multiply both sides by root 3 over 2. So first we'd have c times root 3 over 2 equals 5. And then we'll multiply that by the reciprocal again to get c by itself. Scroll that down a little. Those cancel, leaving c by itself, and now I have 10 over root 3, or again, if I rationalize the denominator with root 3 over root 3, that will be 10 root 3 over 3. From there, we need to still find, so we have c, so we need to find a. So again, I could use this adjacent side, but this number kind of sucks, and that 5 looks pretty easy. So I think I use sine there, so I'm going to use tangent because I don't really want to involve the hypotenuse. I'd much rather use A and B if they're available, and they are. So let's go tangent of 60 degrees, and that's going to equal the opposite over the adjacent, so 5 over B. And then we'll multiply the B up and divide tangent down. I guess I should replace tangent first. So tangent, remember from up above, we just did that one. That one was root 3 equals 5 over b. And then b root 3 equals 5, or b equals 5 over root 3. And then again, doing the root 3 over root 3 right here, like I've done a few times now, that would be 5 root 3 over 3 if I rationalize the denominator. Yeah, and that would be it on that one. Number 5 is kind of the same idea. With this one, again, when they give you a 60 or a 30 or a 45, they're probably going to be looking for the exact solution like I did on this one. When they want an approximation, you'll see in the directions, give your answer to so many decimal places. So for here, again, let's draw a little sketch of this just to get our brain orientated. So we're going to have kind of a flat triangle, not drawn to scale, but we're going to call this one 11 degrees. And if this is angle B, that means I just decided that that is side B. And then C, the hypotenuse, there's my 90. So that makes this one the 100. And then A is the other one I don't know. So let's see, we have the R, or the hypotenuse. I want to get A and B. So it seems like we could just use sine and cosine for that, right? Because sine is opposite over hypotenuse, and cosine of an angle is adjacent over hypotenuse. So that would seem like the two I would use. I wouldn't use tangent in this case because I don't know A or B, and tangent is the B over A, and I don't have either of those. So again, that's how I'm kind of picking which of the three primary trig functions I'm going to use is just sort of determined by what I know and where I'm trying to get. So let's do that. Sine of 11 degrees, and that's our opposite over our hypotenuse, so that would be B over 100. And then we're just going to multiply up that 100, so we're saying 100 times sine of 11 degrees. And throw that in the calculator, and we get B equals to 4 decimal places, 19.0809. And then we'll do the same thing with cosine and use that to solve for side A. So sine of 11 degrees is going to equal A over, I'm sorry, that should be cosine. I meant it, there we go. Cosine of 11 degrees is going to be A over 100. Multiply up the 100, we get 100 times cosine of 11 degrees equals A, and again, just throwing that in the calculator is all I did. 98.1627 is what I got for A, and that'd be that. Okay, this next one is a little bit tricky. Not too terrible, but a little bit. So find the lengths of the missing sides, and this is just that same definition, side A is opposite angle A, etc. And we're being given this information. So we know side A and we know the ratio. So let's take a look at cosine. B equals 5/13 and figure out what that means. So cosine of angle B equals 5 over 13. And we know that cosine is the adjacent side over the hypotenuse. What that doesn't mean is that the adjacent side is 5 and the hypotenuse is 13. What it means is the ratio of these two sides is 13. So this could be 10 and this could be 26, this could be 15 and this could be 39. We don't know the actual lengths of the sides. That's going to be determined by A here. But we do know the ratio of the sides, so we have to be a little bit careful with that. And so instead of calling this A and C in my triangle, and let me draw this triangle real quick over here. We have some angle B, and so let me call that angle B, that I don't know what it is. I know the adjacent side, which would be the opposite side has to be B, right? So that makes this one the adjacent, and it makes this one C over here. I'm not going to call them A, B, and C. I'm actually going to call them A sub 1, B sub 1, and C sub 1, and you'll see why in a second. The adjacent side, at least in terms of the ratios, that's going to be 5. I don't know this one. I do know that the hypotenuse on this is 13. And then let me draw a second triangle to show you what I mean by the ratios. Pretend like those are the same shape. This one is just bigger. So this is still angle B. And this one, it told me that side A is 15. And so you can see there, it's going to be 3 times bigger. So without doing any math, I can actually know that this C is going to come out to 39. I'll prove it here in a second. And then I could use the Pythagorean theorem to find this other side. So that would definitely be one way to do that. I'm going to go through a little more math than that just to kind of show how you can get there if you can't spot it's something as straightforward as multiply this one by everything's 3 times bigger is essentially the what's going to happen. But let me show you how to get there. First off, no matter what, we would need to find some version of b. So let's do that. So I'm going to go a sub 1 squared plus b sub 1, I wrote a 2, because I was about to write the squared, b sub 1 squared equals c sub 1 squared. So let me finish getting my ratios over here, and I'll apply it to this side. So a sub 1 is our 5, yes. B is what I'm trying to work out, and C is 13. Oops, don't need that. And so then B sub 1 squared is going to be the 169 minus 25 again, which is 144. And we see that we run into this triangle a lot because it's easy numbers. Take the root of both sides, and then that tells me B sub 1 is equal to 12. So now we can throw that right there. Without doing any more math, if I can recognize that this triangle is just this triangle blown up by 3, that means this side's going to come out to 39, and 3 times 12, this side is going to come out to 36. And I'll go ahead and show that with the trig, or with similar triangles, in the event that you need to actually, if something isn't quite as clear as that, and you need a little bit more algebraic way to get there. All I'm doing is setting up the same ratios that I'm doing in my head, looking at these two diagrams. But if I say the ratio of a to a sub 1 is going to have to equal the ratio of b to b sub 1, would be one way of setting up these ratios. So a I knew to be 5, and I'm sorry, 15. A I knew to be 15, a sub 1 I knew to be 5. B over here is what I was trying to solve for, and back here I found that b sub 1 is 12. And so here if we go 5 into 15, that would be 3, b over 12, multiply up to 12, and there's the 36. So this is the arithmetic that I'm doing in my head, just looking at the pictures. And I can do the same thing and say a over a sub 1 is going to equal, the ratios will be equal to c over c sub 1. So same 15 over 5, and that's going to equal the thing I don't know, this side over the 13 that they gave me back in the problem. And so this would reduce to 3 c over 13, and then multiplying that up, you see I get the same number that I got just looking at the pictures. There's that same 39. So this is just the arithmetic that supports what I can do from the drawing. And I guess if it was like maybe some ugly decimals, that might be a little harder, but you could always, it's just two different versions of looking at similar triangles. Okay, so next we have the cofunction identities, and this is why I think when you first learn trig, you want sine to go with secant, and you want cosine to go with cosecant, and they don't. This is how come. It's because sine is actually, cosine is the cofunction to sine, cotangent is the cofunction to tangent, and then cosecant is the cofunction to secant. So that's why that naming strategy didn't necessarily makes sense when we saw it back in, I think it was 5.3. And what this says is that sine of an angle is equal to cosine of 90 minus that angle. And I'll just use sine and cosine for instance. Let me go way back to this unit circle for a second. So sine of an angle, so like sine of 30 degrees is 1/2, is going to be equal to 90 minus 30 degrees, cosine of 90 minus 30 degrees. 90 minus 30 is 60, and if you look right here, cosine is 1/2 there, sine is 1/2 there. So that's what that identity is showing, is if I have the sine of 30, it's going to equal cosine of 90 minus 30, which would be 60, and sure enough it does. Again, if you want to see a nice proof of this, Leo does a really good one in his video. I'm not going to redo all that since there's a video posted on it already. but we can use that to evaluate some things pretty easily. So in this case, I have secant of 70, and I'm asked to find what would be equal to that in terms of cosecant. And you can see secant of 70 would be 90 minus 70, or cosecant of 20. So those are both going to be equivalent, which means if I have one, I could replace it with the other if I found that convenient. Here, cosine of pi over 3 is going to be equal to what in terms of sine? These are a little bit harder, so let's go ahead and do a tiny bit of work for that. And if you can see, it's going to be pi over 6. That's great. I'll just show the arithmetic to get there. So if I have, actually get rid of that, 90 minus pi over 3, 90 is pi over 2 in radians, and we're going minus pi over 3. So just do a little review of fractions here. So this would be 3 over 3 to get to a common denominator, and this will be 2 over 2 to get to a common denominator. So that will be 3 pi over 6 minus 2 pi over 6, and there's our pi over 6. And so that would be pi over 6. And, you know, this is right 60 degrees, so it would be 30 degrees, which is our pi over 6. Lastly, in this section, we have just a few examples using the right triangle trig for some application problems. A couple of definitions. So angles of elevation are measured from a given point to the higher elevation. So if I was standing on the ground and it said the angle of elevation to the top of this tower is, 27 degrees, that's showing what it's measuring. If I was at the top of the tower and it was saying the angle of depression from the tower to the ground is 27 degrees, this is what I'd be measuring. So just to help with the drawings that are coming up, there's those two definitions. So for this one, we have the angle of elevation of the sun is 63.5 degrees when a building casts a shadow that long. What is the height of the building rounded to the nearest foot? So let's see if I can draw this halfway decent over here. Here's going to be the top of my building. And this is going to be the shadow, so the sun is right there. And the angle of elevation is measured from the ground up, so that's going to be right here, the 63.5 degrees. And then the shadow cast, the building would cast a shadow this way, so that's going to be 42.9 feet. And I am supposed to find h, the height of the building. So let's see, I happen to know in this case I'm looking for the opposite side from this angle, and I know the adjacent. So if it's opposite and adjacent, I probably want to use tangent. So tangent of 63.5 degrees is going to equal the opposite side, the thing I don't know, over the adjacent side, 42.9. So I'll just multiply that 42.9 up, multiply that by tangent of 63.5, and throw all that into a calculator. And when I did that, I got 86.0, rounded to 1/10 of a foot for those particular numbers. And that's it. The drawing is really helpful, so I definitely encourage the drawing. Number 9, from the basket of a hot air balloon 95 feet above the ground, the angle of depression, so this time we're measuring from the balloon down, of a point A on the ground is 11.5 degrees, was a distance from point A on the ground to the basket of the balloon. So let's get that drawn so we can see what we're looking at. So I'm going to have this is my balloon, and we're going to be, there's my horizontal, and here's my ground. And our balloon is 95 feet above the ground. And then the angle of depression is 11.5 degrees to point A. So we're going to call that point A. I'll try to draw a straight line. So not drawn to scale at all, but that's 11.5 degrees. You may remember from some geometry class in your past that opposite interior angles are equal to each other, so this one is also 11.5 degrees. And we are trying to find the distance from point A to the balloon. And so that is that distance right there is what I'm trying to find. And so if this is a right triangle, this would be, that's the hypotenuse, so that's C. And I know, let's see, I have the opposite side from the angle, and I want the hypotenuse, so opposite and hypotenuse is sine, remember from our, so sine is opposite over hypotenuse. So that's going to let me know which one of the three trig functions I probably want to use. So sine is going to be 11.5 degrees. And opposite is 95. And I'm trying to find the hypotenuse C. So again, we'll multiply with the C, divide the sine of 11.5. That gets us right here, 95 over sine of 11.5. And chunk all that into a calculator, and just round to the nearest whole number. So for that one, I got 477 feet when I did it. And then last one, not too tricky other than it has one little thing that you need to know, and that one little thing is in 1 mile, there are 5,280 feet. And if there's ever a test question where you need to know that, I would give that information. That is not something you need to memorize. So having said that, let's read the problem. Angle of elevation to the top of the building is found to be 8 degrees from the ground at a distance of 2 miles from the base of the building. So notice that was miles. Find the height in the building to the nearest foot. So you got to watch out when they give you units that aren't the same. So let's go ahead and do a little sketch here. So I got this big triangle. I know that this is 8 degrees in there. I know that this is 2 miles to the building. And so if I go 2 times 5,280, then that means in feet, because I want my answer to come out in feet. So I'm just going to convert these miles to feet. That would be 10,560 feet for this adjacent side. And I want to know H. So seems like a job for tangent again, because I'm looking for the opposite and I know the adjacent. So we'll go tangent of 8 degrees equals opposite H over adjacent 10,560. Multiply that up, throw it in a calculator. Hopefully that's getting to be old hat now. And I got 1484 when I put that in the calculator. Cool, that concludes 5.4.